Designing regenerative urban models, resource cycling. Regenerative design education requires more than understanding circularity strategies. It demands the ability to recognize cities as complex socio-ecological systems. Students must learn how to analyze flows, water, nutrients, materials, carbon, and identify where linearity causes ecological degradation. Pinto et al., 2023, emphasize that regenerative outcomes depend on the integration of ecological function, spatial planning, and community engagement. Learning objectives therefore include 1. Diagnosing metabolic inefficiencies, 2. Designing infrastructures that mimic natural cycles, 3. Applying NBS in diverse contexts, and 4. Utilizing digital tools that support long-term monitoring and adaptation. Tools such as BIM, LCA, and environmental performance metrics help designers understand how decisions affect carbon cycles, material longevity, and ecosystem integrity. Sade et al., 2022. An important component of regenerative training is recognizing that ecological processes operate across temporal and spatial scales. Soil formation may take decades, hydrological cycles operate at watershed scale, and biodiversity corridors require regional connectivity. Regenerative education prepares practitioners not simply to design green spaces, but to orchestrate systemic transformations. Regenerative urbanism represents a fundamental rethinking of how cities interact with ecological systems. Unlike sustainability, which is typically framed around limiting damage or improving efficiency, regenerative design sets more ambitious goals: to restore natural processes, rebuild degraded ecologies, and strengthen long-term resilience. In this perspective, cities are not static settlements, but dynamic metabolic organisms whose flows of materials, water, and energy can be reorganized to support ecological renewal. Munonye and Ajonye, 2024, emphasize that regeneration extends beyond circularity because it focuses on the quality and function of ecological systems, not merely the speed or efficiency of resource loops. Nature-based solutions, NBS, play a central role in this transition by embedding hydrological, biological, and climatic processes directly into urban form. Atanasova et al., 2021. As climate change accelerates, regenerative urban models present an opportunity to reposition cities as contributors to ecosystem stability, actively repairing soils, replenishing water cycles, supporting biodiversity, and improving microclimates. This shift reflects a broader transition from anthropocentric to ecocentric planning, in which urban development is guided by ecosystem dynamics rather than by extractive economic priorities. At the core of regenerative urbanism lies the principle of resource cycling. In traditional linear models, resources move in one direction, from extraction to consumption to disposal, creating environmental burdens and requiring constant inflows. Regenerative systems transform this paradigm by establishing loops that return resources back into productive processes. However, the regenerative approach goes beyond typical circular strategies by linking these loops with ecological renewal. Singhvi et al., 2025, identify spatially localized loops, higher density development, and metabolic infrastructure as the basis for circular cities. In regenerative systems, these loops restore rather than simply conserve resources. Compost rebuilds soil, vegetated systems cleanse stormwater, and reclaimed building materials reduce ecological extraction pressures. According to Train et al., 2025, the European Green Deal provides a policy framework for integrating resource cycling into climate-neutral urban development. The regenerative perspective views each urban subsystem, energy, water, food, materials, not as a separate sector, but as a part of an interconnected metabolism. When resource flows mimic ecological cycles, they create resiliency multipliers. Water retained in soils reduces urban heat, healthy vegetation improves air quality, and local material reuse strengthens social and economic stability. Transitioning from sustainability to regeneration marks a shift from mitigation to transformation. Sustainability is often understood as doing less harm, which may improve efficiency or reduce resource use, but rarely restores ecological health. Regenerative cities pursue net positive outcomes, meaning they actively rebuild ecological capacity. Mounonnier and Adjonier, 2024, argue that regenerative cities embed circularity within all spatial scales, from building components to landscape systems. Atanasova et al., 2021, demonstrate that NBS, such as wetlands, urban forests, and sponge landscapes, enable restoration of hydrological cycles, improve water quality, and expand vegetation cover. Unlike sustainable systems that prioritize efficiency, regenerative systems restore soil organic matter, enhance carbon sequestration, expand biodiversity habitats, and improve ecosystem functioning. They operate on the principle that high-performance urban systems should benefit, not burden, the ecosystems that support them. Regeneration requires long-term thinking, recognizing that ecological processes cannot be optimized immediately, but must be nurtured as part of living systems. This shift marks a cultural transformation in urban planning, positioning cities as partners in ecological renewal. While circularity and regeneration share synergies, their goals are fundamentally different. Circularity aims to keep resources in circulation through reuse, remanufacturing, and recycling. Regeneration focuses on rebuilding ecological capacity, soil fertility, hydrological resilience, biodiversity richness, and carbon stability. Singhvi et al., 2025, argue that circular urbanism requires spatially embedded loops and metabolic infrastructure. Regeneration enhances this by integrating biological processes into these loops. For instance, recycling materials is circular, but using compost to regenerate degraded soils is regenerative. Greywater reuse is circular, but redirecting that water into infiltration landscapes that recharge aquifers is regenerative. Regeneration therefore encompasses circularity, but also demands ecological function and renewal. The interdependence of these concepts matters. Circularity without ecological restoration may prolong resource efficiency without improving environmental quality, while regeneration without circularity risks overwhelming ecosystems through continued extraction. The ideal future city integrates both, cycling resources efficiently while strengthening the ecological systems that sustain them. Urban metabolism provides a powerful structure for analyzing how cities transform and circulate resources. It conceptualizes cities as organisms with inputs, energy, water, materials, throughputs, consumption, transformation, and outputs, waste, emissions, heat. Regenerative design reconfigures this metabolism by minimizing external inputs and eliminating harmful outputs through internal cycles. Ecological et al., 2023, demonstrate how urban mining and maker districts recover materials from the existing building stock, reducing the need for new resource extraction. Hydrological redesign, through permeable surfaces, infiltration basins, and decentralized stormwater systems, restores natural water flows. Bowman et al. 2020. Urban metabolism also reveals hidden flows such as waste heat, nutrient streams, and biological productivity. In regenerative cities, these flows are harnessed rather than discarded. Heat becomes an energy source, Organic waste becomes soil, stormwater becomes groundwater stock, and vegetation becomes climate infrastructure. A metabolic framing allows urban designers to view cities not as static built environments, but as dynamic ecosystems whose health depends on the quality of resource exchanges. Water is one of the most influential elements shaping regenerative cities because hydrological processes underpin climate regulation, vegetation growth, soil development, and biodiversity. Regenerative water systems break away from traditional drainage infrastructure, which rapidly channels stormwater away from urban surfaces. Instead, they support slow, landscape-driven flows that maximize infiltration, evapotranspiration, purification, and cooling. Nature-based systems, bioswales, wetlands, urban ponds, infiltration gardens, provide distributed flood protection while strengthening ecological performance. Smart NBS integrates sensing technologies to monitor water levels, soil moisture, and vegetation health. Koiv et al. 2024. Bohman et al. 2020 demonstrate that sustainable stormwater management embedded into planning significantly increases climate resilience. Water reuse, greywater systems, rainwater harvesting, and wastewater recovery further reinforce hydrological loops. When water cycles function as living ecological systems rather than drainage problems, cities experience reduced heat stress, healthier soils, increased vegetation vitality, and enhanced biodiversity. Regenerative material cycles extend beyond the goals of recycling to emphasize durability, adaptability, biological regeneration, and design for disassembly. Sade et al. 2022 show that combining LCA with circularity metrics enables designers to evaluate how building materials support or hinder regenerative outcomes. Urban mining, recovering reusable materials from existing building stock, reduces extraction pressures and extends product lifespans. El-Wakil et al. 2023. Regenerative systems emphasize biomaterials such as cross-laminated timber, mycelium composites, bamboo, and biodegradable polymers that integrate into natural processes. Organic waste streams, compost, mulch, biochar, regenerate soils and enhance urban carbon sinks. Repair economies, reuse hubs, and local manufacturing ecosystems create social dimensions of regeneration by strengthening community resilience and reducing resource dependency. Material cycles thus operate across technical and biological domains, forming a regenerative infrastructure that reduces degradation and increases ecological productivity. Energy loops in regenerative cities prioritize decentralization, renewability, and integration with ecological processes. Solar, geothermal, and wind systems provide distributed energy production that reduces dependency on centralized grids. Vegetated roofs and rooftop greenhouses lower cooling loads, enhance insulation, and contribute to microclimate stabilization. Golami et al. 2020. District heating, microgrids, and energy-sharing communities facilitate collective energy resilience. Regenerative energy systems emphasize adaptive capacity, the ability to shift flows seasonally, use waste heat, and coordinate supply with ecological cycles. When energy systems intersect with material, water, and organic loops, they form synergistic infrastructures. Waste heat warms greenhouses, vegetated surfaces reduce cooling demand, and soil moisture increases evaporative cooling. These synergies reveal that regenerative energy is not only about renewable generation, but about aligning energy flows with ecological function. Organic and food loops form a crucial dimension of regenerative cities because they reconnect urban systems with nutrient cycles that historically operated outside city boundaries. Modern industrial food systems have created long and fragile supply chains that externalize ecological degradation. Regenerative urbanism seeks to shorten these chains and reintegrate biological processes into the urban fabric. Urban agriculture, whether in the form of rooftop farms, community gardens, vertical growing systems, or peri-urban agroforestry, plays a central role by increasing local food autonomy and reducing transportation emissions. Organic waste, instead of being landfilled or incinerated, becomes a regenerative resource through composting, anaerobic digestion, or vermiculture. These processes create soil amendments that rebuild soil structure, enhance microbial diversity, and improve moisture retention, which in turn strengthens vegetation health and stormwater infiltration. Golami et al., 2020. Highlight how integrated greenhouse systems can utilize waste heat from buildings, forming a symbiotic relationship between urban energy cycles and food production. When food loops intersect with hydrological and material cycles, the benefits multiply. Compost-amended soils absorb stormwater more effectively, decreasing flood risk. Vegetated systems cool the city through evapotranspiration, and localized production strengthens community cohesion. Organic loops also serve as pathways for environmental education, enabling residents to develop ecological literacy while participating in community stewardship. Ultimately, embedding food systems within cities does not only produce food, it regenerates soils, strengthens social networks, and realigns urban metabolism with ecological processes. Regeneration occurs across multiple scales, and effective urban design must interconnect micro, meso, and macro layers of ecological and infrastructural systems. At the building scale, regenerative features include green roofs, passive ventilation, rainwater harvesting, greywater reuse, reversible or modular construction, and indoor ecological systems such as green walls and microhabitats that improve air quality. At the neighborhood scale, regenerative infrastructures take the form of shared composting hubs, distributed energy storage, community-managed gardens, infiltration corridors, slow mobility networks, and circular makerspaces that support local repair and reuse ecosystems. Pinto et al., 2023, emphasize that regeneration is not possible without community engagement. Shared infrastructures only work when residents collectively maintain them. At the city scale, blue-green networks, ecological corridors, constructed wetlands, restored waterways, and permeable public spaces create metabolic and ecological continuity. Singhvi et al., 2025, demonstrate that spatial adjacency between material hubs, water infrastructures, and vegetated landscapes is essential for effective circularity and regeneration. At the regional scale, cities must collaborate with surrounding forests, watersheds, and agricultural landscapes to maintain ecosystem services such as flood protection, pollination, groundwater recharge, and climate moderation. The multi-scalar nature of regeneration ensures that solutions do not operate in isolation. Instead, regenerative infrastructures function as interconnected ecological technological systems capable of producing cumulative, long-term environmental benefits. Public space becomes a powerful regenerative medium when designed to operate as a living ecological infrastructure. Conventional public spaces often prioritize aesthetics, circulation, and recreational uses without integrating ecological processes. Regenerative public space design expands this thinking by making soil formation, evapotranspiration, habitat creation, stormwater infiltration, and microclimate regulation primary design drivers. Vegetation-rich public spaces mitigate the urban heat island effect, improve thermal comfort, and support local biodiversity. Yilmaz and Ozturk, 2023. Meanwhile, Atanasova et al., 2021, show that NBS, such as rain gardens, bioswales, green corridors, and urban meadows embedded within public spaces, encourage ecological connectivity and enhance environmental performance. These landscapes sequester carbon, improve air quality, and provide habitat for pollinators and small fauna. Regenerative public spaces are also deeply social. They promote mental health, foster community interactions, and support cultural practices. When equipped with educational signage, demonstration areas, or community-managed ecological zones, public spaces become platforms for environmental learning. The multifunctionality of regenerative public space arises from its ability to merge ecological restoration with aesthetic, social, and climatic functions, creating urban landscapes that are both beautiful and biologically productive. Regeneration does not succeed through design alone. It requires robust governance frameworks, long-term policy support, and active community participation. Policies aligned with the European Green Deal promote climate neutrality, circularity, biodiversity enhancement, and nature restoration, providing essential support for regenerative transitions. Train et al., 2025. These policies encourage municipalities to adopt circular procurement, integrate NBS into planning regulations, and provide incentives for decentralized renewable energy, local repair networks, and community-based resource systems. According to Pinto et al., 2023, regeneration depends on participatory processes because ecological infrastructures require ongoing stewardship. Top-down planning can implement physical infrastructures, but cannot guarantee long-term maintenance without local engagement. Governance for regeneration must therefore support co-management models, where communities influence design decisions, assume stewardship roles, and benefit from the ecological improvements. Additionally, governance must enable cross-sector collaboration, uniting water authorities, waste managers, energy providers, social organizations, and environmental agencies. Regenerative governance is adaptive, integrative, and long-term, recognizing that ecological outcomes unfold over decades. Without policy continuity and community ownership, regenerative systems risk becoming isolated pilot projects rather than citywide transformations. Measuring regeneration requires indicators that capture the depth, complexity, and long-term evolutionary nature of ecological processes. Traditional sustainability metrics, such as energy use or emissions, do not fully reflect regenerative outcomes because they focus on efficiency rather than ecological renewal. Regenerative indicators include soil organic matter and microbial activity, measuring soil health and carbon sequestration potential, infiltration rates, evapotranspiration performance, and water balance indices, capturing hydrological function, biodiversity richness, and habitat connectivity scores, evaluating ecological networks. Material circularity indicators integrated with LCA. Sade et al., 2022. Vegetation canopy density and cooling potential, measuring climatic performance. Community engagement and stewardship participation, reflecting social resilience. Resilience metrics, assessing redundancy, diversity, and adaptive capacity. Atanasova et al., 2021. Emphasize that ecological indicators must reflect system functionality rather than static snapshots. Measuring regeneration means tracking whether urban systems are evolving toward greater ecological performance, not merely maintaining stability. Robust indicators allow cities to monitor progress, guide investments, and ensure that regeneration translates into tangible environmental improvements. Digital technologies significantly enhance regenerative design by supporting simulation, monitoring, data analysis, and long-term adaptation. Building Information Modeling, BIM, enables material tracking and design for disassembly, making future reuse easier. Life Cycle Assessment, LCA, evaluates environmental impacts across a building's lifespan, supporting regenerative material choices. Digital twins simulate hydrological performance, energy flows, and ecological interactions under various climate scenarios, allowing designers to optimize regenerative potential before construction. Sensor-based monitoring systems, such as soil moisture probes, water level sensors, thermal cameras, and vegetation health detectors, support adaptive management of NBS and other regenerative infrastructures, Koiv et al., 2024. When integrated into digital dashboards, these tools provide real-time feedback that helps municipalities identify stresses, inefficiencies, or failures. This ensures that regenerative systems are not static installations, but evolving infrastructures capable of adjusting to changing conditions. Digital tools therefore become critical bridges between ecological processes and human decision-making, enhancing transparency, responsiveness, and long-term resilience. Several notable case studies demonstrate that regenerative urbanism is not theoretical. It is already being implemented across diverse contexts. Hammarby Sjöstad, Stockholm, integrates water, waste, and energy loops into a closed metabolic model. Waste heat becomes a resource, stormwater is treated through natural systems, and waste materials are reused or converted into biogas. Kalundborg, Denmark, represents the world's leading example of industrial symbiosis. Waste streams, steam, wastewater, gypsum, heat, move between industries as resources, forming a regenerative industrial ecosystem. Ecological et al., 2023. Utrecht, Netherlands, implements citywide blue-green corridors that improve infiltration, restore biodiversity pathways, and reduce urban heat. The city demonstrates how ecological networks can structure urban growth. Singapore's new water system illustrates advanced water looping through high-grade reclaimed water, showcasing regenerative potential in dense, resource-constrained contexts. These cases show that regeneration can occur across scales, from industrial districts to entire metropolitan regions, and that integrated systems thinking produces measurable environmental and social benefits. Regenerative urbanism redefines the relationship between urban development and ecological processes. It integrates circular resource loops, NBS, decentralized infrastructures, community stewardship, and digital tools into unified frameworks. As Pinto et al., 2023, note, regeneration succeeds only when ecological, technological, and social dimensions work synergistically. Circularity alone is insufficient unless it results in ecological renewal. Regeneration demands the revitalization of soils, restoration of water cycles, enhancement of biodiversity, and decarbonization of energy systems. Through these combined strategies, regenerative cities evolve into resilient, adaptive ecosystems that strengthen both human and non-human life. Urban resilience, community well-being, and ecological vitality are no longer separate goals, but interdependent outcomes of regenerative design. Regenerative urbanism represents one of the most ambitious and transformative paradigms in contemporary planning. It challenges cities to move beyond minimizing harm toward actively repairing ecological systems. This requires new forms of governance, innovative technologies, multi-layered infrastructures, and cultural shifts in how communities perceive and interact with nature. Regenerative models treat cities as living ecosystems, whose survival depends on their ability to circulate resources, restore natural processes, and cultivate mutualistic relationships between human and ecological systems.